All right. So this page actually, there's a pre-lecture. I sent out an email today, so I apologize that the typo, what was there, half of you could get to the number that was there. I recorded back in October, so I can fit all this into my less than normal time, where I talk about the electromagnetic spectrum. And so it actually is on our playlist on YouTube. There's a reason, I think, because my other classes, I can't go from newest things to oldest. It would actually mess up for our playlist too. So anyway, I would encourage you to watch it sometime in the week. You can wait until Friday when it's a rainy day. So this page, it's going to review some of that, and we're going to do math for the next hour. And you can see this is going to be algebra again with some interesting symbols. So we're going to go through the symbols on this page, and the video might make more sense after we go through this stuff. I might refer back to some of the things. This is really cool. Max Planck, the whole term, the matrix that everybody's always talking about, he's the guy who coined the phrase. Not quite, because I'm pretty sure it shows up in the Old Testament several times. And so that's where he got the word from. All right. So why we're talking about light, why there's all this, why I'm rainbowed out and get into this whole thing, is to understand what quantum mechanics is it's the study of electrons and how electrons behave, because they don't behave like Sir Isaac Newton said they would. And so to understand how an electron behaves, we have to talk about light. And I only get to briefly talk about it, but light there's that whole, and that's a whole nother thing that we call it the dual nature of light, because we're into dualism for some reason. We have good and bad. So there's a dual nature that light is a wave and light is a particle. And so Maxwell was the guy who came up with this equation that C is the speed of light, which is roughly 3, or for our purposes, we're going to use 2.998 times 10 to the 8th meters per second. So we're using meters per second. You can also do it in inches, but we're going to do it like that. So we have 4 sig figs. This is a lambda. It's a Greek letter, and it is wavelength. So light moves in waves, and I talk about this in the video, and a wavelength is from one crest to the next. And so that is the wavelength. And so that's going to be a distance. So typically that is in meters. And then the traditional symbol for frequency was the VU symbol. However, too many students and people, as they moved on, got that mixed up with velocity, and they're not the same thing. So in physics, they've actually moved to using it's like a funky F, a lowercase f. In chemistry, they still show this. So you're going to see me go back and forth. I don't care which symbol you use. I've been slowly reverting to the F, but you'll see it both ways. And frequency is if you were standing in one place. So if this is me standing here, how many waves pass me per second? So it's cycles per second, but technically the units are just seconds to the -1 or per second. So we leave out the term cycle, which is what they're saying, how many waves. So if you're standing at the beach and counting waves, that's the idea. Right. So to use the formula is we have a yellow line. And so I'm going to go back a page just real quick. And the visible spectrum, sorry, so they just threw the spices in the food that is being cooked, and it's wonderful. I love spicy food, but it chokes me up when it's being heated. Visible means what we as humans can see. We see such a really narrow band of this whole thing. Yeah, this was just kind of a cool picture. You can see it all different ways. But for visible light, and this is what I talk about is in the video, everybody pretty much as little kids learns Roy G. Biv. So this is going from red to V is violet. Purple is a color that was made up by Crayola. So most colors were actually made up by Crayola. And what Maxwell said is everything. We can go past red into infrared. We can go past violet into ultraviolet. And actually, for the study set, as we go through other stuff today, you're going to want to watch that video because I talk about this spectrum in there. That the red end is the longer wavelength. And violet is where we get into the shorter wavelength. So ultraviolet just means beyond violet, and infrared is beyond red. And so we can't see the infrared and the ultraviolet, but they're used. Ultraviolet's used, right, for people will use it as a way to sterilize their water. And there's a reason, and we'll get into that. Infrared's used as a heat lamp. This is just the colors that we as humans see. So the relationship, this formula is C equals wavelength times frequency, which we're going to solve for. Since C is a constant, and for our purposes, we're going to keep it as a constant. As you increase the wavelength, you're going to decrease the frequency. So as wavelength goes up, so the longer the wavelength, the lower the frequency. And this is going to have a higher, the short wavelengths are going to have a higher frequency. So you're going to have more passing you every second. And that's actually becomes significant. For visible, what we can see is in nanometers, and that's why it's hard writing as Roy G. Biv. Violet is around 350-ish nanometers. Some people can only see to about 400 nanometers. Girls can usually see a little bit further than guys because if you look anthropologically, whatever you want to believe in, we had to go and distinguish between like berries and stuff, where guys usually have, they were the hunters and the women would have been the gatherers. So there's a different distinguishing of colors in there. And then red is about 700 nanometers. So we're going to be using nano a lot. And of course, you guys, everything's take home, so you can always Google, although that takes time. All right, so remembering the order of your rainbow. And again, in the video, I talk about it and go through this. And then I do my favorite demo of the year, which was really fun. All right. So we're going to plug in. We're going to state our formula. C equals wavelength times frequency. And again, you can use the V or you can use the F for frequency. So we're solving for frequency. So rearrange C divided by the wavelength will equal frequency. You can just say C as C, or you can plug the number in. I'm going to plug the number in this time. And that is, for many of you, you may want to initially, because that's really important to know your units. If we're going to be dividing by 589 nanometers, we do need to change our nanometers to meters. So 10 to the negative 9th meters per nanometer. So nano is probably Latin for 9. Or something like that. So nanoparticles, they're in that size. And that's actually interesting because that's the size of atoms. And is it a coincidence? That's also the size of the wavelengths that we see as humans is in the nano range, which is also the size of atoms. You can ponder that. And the units you will get will be, 5.09 e to the 14th. And the meters will cancel. Our nanometers cancel. You'll be left with per second. I talk about this in the video also. the abbreviation for seconds, the correct unit is just an S. I guarantee most of you, if you write S, you're going to think it's a 5, and you're going to do really funny math. And then you're going to say, I'm never going to abbreviate it as S again. So I always write sec. When I sat through Dave Faust's class, he always did that too. And it's probably that we learned from practice and from watching students that they think it's a 5. It's the same with like oxygen. When I write it, it looks like a 0, and then students get confused. So seconds, you can write it like this. It means seconds to the -1. And what that unit is a hertz. So Hz is hertz. You've probably heard of hertz. So that's a frequency. The old, right, if you listen to radios, they always have a different wavelength that, like, you tune your radio to 89.1. That was a certain hertz that you were turning it to. So it was the wavelength of the radio waves. Anyway, so pretty simple. So that was Maxwell. And then Max Planck came along. And his uncle, I talk about this in the video a little bit. His uncle and his father were both pretty distinguished physicists. And they told him not to go into physics. Don't go into science. They told him to go into music. So Damon's going to appreciate that. They told him, go play the violin. Everything has been figured out. There's nothing more to figure out. And so here we are 120 years later, and we're like trying to figure out every little detail. So it's kind of like we swung the pendulum too far the other way. But Max didn't listen to them. And the Max Planck Institute is the biggest science institute in Germany. So it'd be like our Harvard or something like that. And there was still an unknown phenomena, which was the ultraviolet catastrophe. So basically, Maxwell, the simplistic way I think about it is Maxwell said, he kind of made this a communistic thing, and he said all wavelengths have the exact same energy. And so everything is distributed equally. So even though the wavelength and frequency is different, he said, but they all have the same energy. And Max Planck was the one who said, what if they don't? And then he came up with this equation and his constant. So this is called the Plunk Constant. He didn't name it after himself. And I don't know why it gets an H. It's probably some German word in there. It has a funky unit because constants always have weird units so that they cancel everything else out. But he said, he showed that they don't, that wavelengths do not have the same energy. And that's actually a huge concept also to get. And that's where I said the big picture. So this is his formula. So again, we'll do the math with it. But as energy, excuse me, as energy increases, frequency will increase. If you, it was back in the second or third week when we first talked about moles, there was a little video I made, and I talked about the size of the number, Avogadro's number, which we're going to get to use down here, so don't worry. That was to the 23rd. This is to the -34th. The size of this number, the magnitude of it, like, it's really inconceivable, but it is what a quanta is. And Max Planck coined the term quanta, and that's where quantum mechanics comes from. But the big picture is, again, as you increase wavelength, you decrease frequency. That would mean you also decrease the energy. That becomes important when we get down here. So the longer the wavelength, when we get to red and infrared, the wavelength is getting longer. They have less energy. When we get to the shorter wavelengths, like violet and then ultraviolet, and then beyond there, which is after ultraviolet, you get to X-rays, you get to, I didn't know there were soft and hard X-rays. There's gamma rays, there's the cosmic rays. And so we're getting into the ones that cause damage. So these guys are the ones that damage us, right? We have that whole fear of ultraviolet light's going to give us skin cancer and stuff, because it could. whereas infrared light is not going to do that. And the reason is the longer wavelength, microwave, past infrared is microwave, past microwave is radio wave. I do this on the board. I have the 2-3 boards I keep talking about, so I can make a huge spectrum. Anyway, so these don't cause the damage because they're longer wavelength and lower frequencies, so they're lower energy at this end. And so again, that's trying to show that middle part there. Pens are not working well. Is the wavelengths. These are just trying to show you examples to compare to the size of the magnitude of these wavelengths. All right, so the big picture, what has greater energy, ultraviolet or infrared? Ultraviolet, because it's a shorter wavelength. Yellow or red, so again, Roy G. Biv. If you don't know that acronym, so red is longer, that's our higher wavelength. So red is going to be the lower energy, so yellow has the greater. So on your study set for Thursday, some of the first questions are this. And yes, of course, you can just Google it and get it, but you should, 20 years ago when I started teaching, there wasn't this whole, everybody would Google everything, and they actually learned this and understood the relationship. And then here, so microwaves are what we use for cooking. And again, I talk about all this in the video. So green is going to be at the higher energy end of that. So do watch the video, watch it after class, you'll watch it now. I think it's only like 20 minutes or something. Because last 5 minutes I'm doing a cool demo. All right, so we're getting solved for energy for our yellow light. And we actually already did the first step. This is step 1. We solved for frequency, so I'm just going to jump to the chase here. This would be our step 2. We would do energy equals h times frequency. So I always break it into steps. That's just how my brain sees it. There is, of course, you can combine these 2 equations into one because they both have frequency in common, and that's great. You just want to state the formula you're using. And so we'll use h 6.626 times 10 to the negative 34th. And this is joules times seconds. And then I'm going to bring in my answer from up above because it's still the same light. 5.09 times 10 to the 14th per second. And so the seconds will cancel and we'll be left with joules. We come up with a really small number, 10 to the negative 19th, because this is a really small number. And so what Max Planck said is that light is moving in packets. So when you look at a rainbow, it looks like a continuous spectrum. You can't distinguish where the red becomes the orange and the orange becomes yellow. You just see the colors and you go, wow, the rainbow, it's so cool. And what Max Planck said, those are actually packets. It's like you and me, we look like a whole being, but suppose we were made up of atoms, which are discrete particles, like really little particles that we can't see. We'd have to have an electron microscope to see them. And so that's the same idea with light, that if you could see the discrete particles, 10 to the negative 34th, you could distinguish then where the red becomes orange. Because each one of those is a slightly different wavelength. All right, so then the third piece here is why Albert Einstein won a Nobel Prize. So it's a little known fact. Most people think he won it for E equals MC squared or for his relativity work or all those cool things, but it was actually for the photoelectric effect. And you all probably use this sometime today, which is when you walk into a store and the door automatically opens. That's an application of this. Scanners are an application of this, which we all use on our phones and stuff. And so Albert Einstein got kicked out of his school, and he was working as like a patent attorney. And so in 1905, he I guess he was sitting there bored doing his work. He came up with a whole bunch of amazing theories, and this was one of them. And this was another issue that was going on, and he built off of Max Planck's comment just a few years before. So this was all going on in Germany, and it is that if you have a metal, so we have a piece of metal, it doesn't matter what it is, if you shine a light on it, let's say you shine a red light, so that's just saying we're shining the red light, nothing happens. You can make it a high intensity light, nothing happens. If you get a blue light, and see, I should have done blue. I keep forgetting I have, do an indigo light. The most missed colors. So if we shine then a blue light on it, we can actually eject an electron. And so the question was, why? We can even do a really dim blue light. But if it's a blue light, that's why blue lasers, you can't really get them because they're going to cause damage. So why is the blue light ejecting an electron and the red light is not? That's why I won a Nobel Prize. It goes back here to the big picture. You guys should all watch that video. It goes back. You got to learn Roy G. Biv. Red is a long wavelength. It doesn't have enough energy. The electrons are being held in that metal by some force, and you have to overcome the energy of that force. The blue light, because it's a lower wavelength, it has a high enough energy, and it has the energy in that quanta, the quanta of energy is enough to knock the electron out. This is before we have the idea of orbitals. That's what we're getting to on the next page. And so, right, he comes up, I cannot remember, and I apologize, who coins the term photons, if it was Einstein or Plunk. I think it might have been Einstein. That what Einstein basically does, if we go back to this, he adds the unit per photon. So this is really per photon. I mean, he didn't actually literally go and add that in there, but I don't know if he coined the term photon, but he said, so a photon is a particle of light. So like an atom is a particle of matter. So I've been talking about atoms the whole term, and people kind of go with it. And then suddenly I say a photon is a particle of light, and people are like, how can you have a particle of light? And it is here that light does not have a mass. It is not matter. It's just waves. But yet, if we have a high enough frequency, it can knock, this is matter. This does have a mass. It can knock, it can dislocate a piece of mass, piece of matter. And that's where this all gets quite interesting. So a photon is a particle of light. So Avogadro's number, which was like 20 years before this, was Avogadro stuff, and Avogadro was just laughed at and stuff. And it was another thing that Einstein did in 1905 that like vindicated Avogadro, and everybody was like, oh my gosh, she was a genius. And that was Brownian motion. But we're gonna take our number from up here because it's still the yellow light. So this is our step 3. And we have 3.37 times 10 to the negative 19 joules. We're gonna add a unit. And that's actually joules per photon. And that's going to allow us to use Avogadro's number because you can actually count photons. So the quanta, that's kind of like what Albert Einstein put with Max Planck's, is that these are packets of light. So particles are packets of light. and you can count them. They're so extremely small. But so we can do Avogadro's number, 6.022 times 10 to the 23 photons is 1 mole. So like we had atoms or we had molecules, photons also gets to use Avogadro's number, and then we would just change 1,000 joules to a kilojoule. And this is why we had to do what we did for the past week. We're in kilojoules. We're talking about energy, and so this is going to be able to relate to what we just did with chemical equations. And so there's our answer, the 203 kilojoules per mole. Like what you did on your homework tonight, the very first answer, it was just negative because it was emitting. This would be absorbing that amount of energy. All right, we'll talk about emitting and absorbing. Go ahead, Skylar.
Like electromagnetivity, like for particle accelerators at CERN and stuff, something like that.
What?
Like electromagnetic fields, isn't that used for like particle accelerators?
Yeah.
At like CERN.
Oh, everything. Yeah. If you go and get an NMR, that's what an NMR is. Or a PET scan is positron emission topography. So all of these things are working with the electromagnetic field. And that's why I keep saying that we're about to change, because we're about to move into the magnetic age, which changes everything. But yeah. So actually, Skylar, thank you for saying that. That actually an innovation topic would be really cool. Look at CERN has an amazing website, and so looking at any of the particle stuff they've done, if somebody wants to look into it, or PET scans or NMRs, yeah, this all comes together in there. But it all goes back to this really simplistic video where having an understanding of the basic layout of this, that red is a longer wavelength, so it's low energy, so it's not going to knock the electron out. When we get to yellow, yellow was a higher energy because it's a shorter wavelength. Anything from yellow beyond was going to work, because green would work, blue, indigo, violet, because they all have a shorter wavelength, which means they have a higher frequency, a higher energy. Past ultraviolet is everything that causes damage, so we get into X-rays and stuff like that. So we're getting shorter and shorter and shorter and shorter. I mean, they're getting infinitesimally small. Again, this in here in the visible is a really small part of this whole electromagnetic. Now, cutting back to what Skylar was asking, past infrared, this is where we're getting really long, is where microwaves are, and then radio waves. And so this is how communication is. The longer wavelengths is where we're communicating. And so we all have a frequency that we actually communicate with. And so it's like tuning your radio. I don't know if any of you have an animal, but you may find that you can actually kind of call your animal without, or you have a friend and you think of the friend and suddenly they call you. And so that's you're putting out a certain frequency. And when you have family and friends, that we also often tune into that. Yeah. All right, let's move on. So that's all these are. And the first half of your homework is just using these equations and then factor label, and then comparing the different, is it longer, is it shorter, is it higher frequency, is it lower frequency? All right. We are going to keep going. So I'm going to pause for 2 minutes and give you a chance. This one works through what we just did, but you're going to go backwards. So you're going to start with the kilojoules per mole. You're going to do factor label. You have to get to joules per photon. Then you can do the E equals H times frequency. And then, then you can do C equals wavelength times frequency. And again, you can use the frequency as the V or the F. I'm going to pause and give you all a few moments. So let's go ahead and solve this. So I'm going to break it into steps because I find for most students, it makes more sense if I break it into steps. If you could do the whole thing factor label actually, if you wanted to, because those these constants have units. So we're going to get to joules because Planck's constant is in joules. So 1,000 or 10 to the third joules per kilojoule. And we have to get to photons. So 1 mole is Avogadro's number of photons. And so this first half of the lecture is talking about light. We're going to get to electrons on the next page, or actually on this page. And that's going to give us the number. If you want, you could do the whole thing in factor label. That would give you a number that you would then, I'm going to do it 2 ways. You could then say that would equal E, which you would then E equals H times frequency. So that will equal E. So step 2, you would take the E divided by H, and that will give you the frequency. So the H was the constant on the previous side. And then step 3, I would just take C divided by the frequency will equal my wavelength. So using this formula. And you should get, and then change its nanometers. And I will ask you, where does it appear in, where is it in the electromagnetic spectrum? So that's going back to this part of this picture that, again, visible, we can see in there. So, you know, 685 is at the longer end, so that's going to be red. You can always Google it, and it might give you something like red, red, orange, or all the colors. Some funky color. I've been trying to decide what wavelength pink is, because neon lights give a pink line. That's what we're talking about now. So the next big thing, which is actually 50 years before these guys, is in the mid 1800s, Kirchhoff, I don't know how to say his name, they were playing with these spectroscopes, and this would have been the lab we would have done this week. And what happens, so a rainbow is the full spectrum, so it's white light, so you see all the colors. Like we see red to violet, but there's other colors there. What they found is if, I think I talked about this if they took a tube, I can't remember the name of this right now. Wow. And they'd put a gas in it, so hydrogen. And then this is hooked up to electricity. So electricity has to happen, and you excite it. Oh, this is actually not quite yet with these guys, but they were able to look, and what happens is you only see, and then if you look through it through a prism, it's like what a raindrop is, but in lab we actually have these prisms. You actually don't see a continuous spectrum of light. You only see specific colors. You see lines, and those lines are just one specific color. And so that's what these numbers below that are really faint and on my thing are out of focus. The 656 is the wavelength of the lines. And so for hydrogen, when we're in lab, it's like you see this when you're looking at this tube, and it has a purple color. You just look at it and it's purple, like I am today. And then you look through the little scope and you suddenly see these 4 lines, and they're very distinct lines. And they are called Sam, Pete, Dave, and Fred. For those of you who want to see where we're going with this on Thursday, which is the SPDF, that's where they came from. So you see, and then if you take a different gas like helium, you see a different set of lines. So helium has 7 lines. And then if you take neon, you see a different set of lines. Neon gives pink. I don't know how it gives pink, but you actually see a pink line because pink isn't really in Roy G. Biv. And so the pink flamingos you see, those are actually neon signs. The blue, see a blue crab like sign, that's actually argon gas. If you saw a purple sign, it's hydrogen gas. So every element has a distinct set of lines. Hydrogen comes out purple because it has several purple lines or violet lines down here. And so the question became why, and this is actually how they discovered helium. So helium is Helios, which means sun. And so the noble gases, this is also when the noble gases start being discovered, is when they looked at the sun, they saw blank lines that they could not identify with any other element. And they realized there had to be another element in the sun that was, I mean, hydrogen's like most of the sun, but it was a significant part. And so those lines they finally realized was helium, and that's where helium got its name. But this became the big question, is why do we only see lines for different gases? Like these, Kirchhoff came up with this elegant experiment, but he didn't really know what it meant. Well, so several guys come along. I left out a whole bunch of notes. I used to spend like the history of this is actually quite fascinating. And they would sit in their basement, and there is a mathematical, if these have numbers, these have wavelengths. They figured out the wavelengths of these 4 lines. Somebody figured out a mathematical connection between them. And so that was Balmer. So it's called the Balmer series, which is he figured out a mathematical number to connect these 4 lines that you see for hydrogen. His number only works for hydrogen. Every element would have a different, because every element has different lines. And then this guy came along called Rydberg, and that's what the R is. And he came up with a sequence. And so his constant, Balmer has another constant, and it's not used, but Rydberg's constant is used, and we're going to be using that. So we're going to use this formula. So the H is Planck's constant, the C is the speed of light, and R is Rydberg's constant, because he noticed there was a way to mathematically calculate it. But the grand genius of them all, who put it all together, who's also the one who helped Rutherford in 1919, because Rutherford could not figure out what his data meant, and Bohr was the one who said, what if? And how is this happening? And he said, what if electrons are in orbits? So he actually called them orbits. This is called the old quantum mechanics, because his quantum mechanics only works for hydrogen. And so the new quantum mechanics is a more elegant equation, and then we call them orbitals. So after this page, we'll be calling them orbitals. But it was Niels Bohr who made the big jump based off of, as Max Planck also did, by having this idea that we could quantize light and the energy and all that. But so one of the things with this is, so if you're a musician, standing waves, so a guitar string has standing waves because it's tied down at both ends. And so if we were holding a rope, so if Major and I had a rope in the class, and so a jump rope, and we could make waves by moving our hands, and if we were moving our arms at a certain frequency together, we would get these waves that would travel across the rope from my end to his and keep going. And then Skylar could come in, and if you look at waves, so if a fixed wave, a standing wave is where the ends are fixed. And a node is a point that's halfway between the peak and the valley. And so these are called nodes. They are a point of no change. So even though my peak will become a valley, like if you guys are watching, the peaks look like they become valleys. If Skylar goes in and grabs one of these nodes, the waves keep going. It has no impact on the waves. So as long as the 2 ends are fixed, and that's the idea of a standing wave. But because of that, because you only have, I have a blank page. I have a blank wall behind me. And I'm not a physics teacher, so I'm not as good as these as the guys online. But if you have, like, from this point to this point, so you have a standing wave, you have a fixed point, we could do 1 wavelength, we could do 2 wavelengths, we could do Did I do that right? We can do 3. So there's only certain numbers that are possible. And that's what he said, that only certain numbers are possible because it's a standing wave. And that's how electrons behave. So he said electrons are behaving like waves, but only certain numbers are possible. When you look at a rainbow, every number is possible. Every possibility of wave is possible. But in a standing wave, you can only have one this size, one this size, or one this size. And that's why we see red and then a green and then a violet and a very specific line and nothing in between. So the lab is so cool because it's electrons jumping around. Another way I read in a book is, he said, think of it like pennies. And if you have pennies and you have 20 pennies and you make a circle with the pennies, the circles can only be certain sizes because you can't have a gap between the pennies. So you can make a circle, say, with 3 pennies, like a triangle, and then you can make one with 4 pennies and then 5 pennies. But there's only certain radii that are possible for the circles you're making. And so that's kind of the same idea here. These nodes are going to come back. And so for right now, we're just going through the math, and then we get into the theory part, which you're going to love. But the math is just numbers. Oh, and so because of that, only certain wavelengths are possible. All right, so the big question is the end. So one thing, and this goes back to what we just did, rather than talking about heat is a form of energy. That we're looking at energy. You can't know the energy, you can only know the change in energy. And so it's energy final minus initial. So what the ends are, what did he call them? So to just keep the terminology, I can't remember right now. My brain in this environment is fascinating. These are going to be the shells, meaning, so if you have, this is our nucleus. You have, that would be n equals 1. That would be n equals 2. This would be n equals 3. I draw beautifully. And so on. So the electron, it's the shell where the electron is, or the orbit of the electron. So another example is onion skin. So when you peel an onion, you have one layer, you have another layer, you have another layer, or staircases or floors of a building. You can be on the first floor, you can be on the second floor, you can be on the third floor. And so you can be in the first shell, you can be in the second one, you can be in the third one. He again called them orbits. We're going to expand on that when we go to the next page. You can't be in between. So the electron cannot be in this space in here. The electron is out here. And so this is not how a string instrument works. I don't know why I have the guitar string because it's attached at the 2 ends. So a guitar, you can move your hand if you play a violin or the fiddle or anything. You can hit every single thing between an A and a B flat by moving to different places on the string. If you play the piano, you can only hit specific notes, or if you play clarinet. If you play the slide trombone, you can hit every single possibility of range of notes because you move the trombone to different slides. But this would be like playing the clarinet or the oboe or piano, that you can only hit specific notes. Or if you're in an elevator, you can only get off on the first floor, second floor, and the third floor. And so as you increase the n, you increase the distance from the nucleus. That's going to keep the same on the next page. On the next page, I call them shells. I'm pretty sure this is what he was calling orbits, because again, why this only works for hydrogen, does anybody know why? ends up being really special for hydrogen, which is a good thing. Hydrogen has how many electrons? Has 1 electron. When we suddenly add a second electron, it does change the game a little bit. NF means the final one, and initial is the initial. So what we're going to do is we're going to put energy in. Electrons don't stay in one place. They move around. So if we, in lab, we plug it into the wall, we send the neon sign, right? So the pink flamingo, you plug it in, and those electrons are getting a whole bunch of volts put through them. If you got plugged into the wall like those neon signs do, you would get pretty excited too. And the electrons jump. And so the electron might have been here, and it makes a jump. It can't jump in between. And that is what a quantum leap is. It cannot jump in between. It cannot walk from here to here. It actually goes from here, and then it's there. And it can never be anywhere in between. It can only be here, here, or here. And so that's what a jump is. And so on this one, it's going from level of n equals 1. So it's on the inside, the electron's here, and we're jumping it out to the 4th level. So we'd go all the way out to 4. So let's just go ahead and go through the math. So delta E equals negative RHC. So that's R. H was on the previous page. C, you don't have to write the numbers out. You can. Most people just write negative RHC, especially in physics, like a lot of constants, we just write them like that. And then we're going to do 1 over n final, which is the 4. So n's are whole numbers. They're just a number. And then 1 over, we started at the first level, so 1 squared. And then it becomes putting it in our calculators. So I put my calculator. Maybe I've done this like a zillion, 20 times before. Really? All right. I'm going to write the numbers out just because I have to show you what happens with the units. So m to the minus 1 means per meters. There is a negative here. That's really important. Although you can use logic, H was 6.626 e to negative 34 joules times seconds per photon. So in chemistry, I always put the per photon. So this is just my RHC, and my C was 2.998 times 10 to the 8th meters per second. I just wanted to show you how the units work out. Again, you never have to write these out. The meters cancel because that's per meter, and that meter is on top. The seconds cancel. And so you are going to be left, when you use this formula, you're going to solve for joules per photon. That's important so you know what step to do next. So when you punch this in, the answer we get should be 4.087 times 10 to the negative 19 joules per photon. This is just number crunching. This is on your study set also, that you get to punch these numbers in. We're not done because the question wanted us to find kilojoules per mole and then to find the wavelength. So how do I go to kilojoules per mole? You know, oh yeah, sorry. I wrote the wrong number down. Sorry, I was looking at 2 examples. It's just the first 3, the times 10 to the negative, it's 2.044. I was doing the next example. I wonder what happened to that example. And this should be to negative 18. I apologize. So 2.044 times 10 to negative 18 joules per photon. So that's what we get from from that part. And so, yes, Major is right. So the next step is we would go to joules to kilojoules, and then Avogadro's number of photons to 1 mole. And that will give us 1,231 kilojoules per mole. There is one other thing I want to point out with my numbers. The answer is positive. You do not need to show the positive, but energy can come out as a positive or a negative. What does a positive energy change mean?
To generate energy?
Opposite. It absorbs. So this absorbed energy. So that is actually key. That's going to be one of the other big concepts. Tonight's lecture, so this is kind of like 2 weeks ago when I first introduced the heat and specific heat, and everybody just looked at me at the end like, oh my God, what language is she speaking? Which I was speaking Greek that night. But after we did more with it, it starts making sense. This is even more like we're speaking alienese or something. And so it's this part is just plugging in numbers. But when you go from inside to outside, meaning from an inner orbital, so from n equals 1 to n equals 4, you are going to absorb energy. So that's another big point of this. So going back up to here, as you increase the n, you're increasing the distance. So we went from the inside to the outside. That's what I meant here. You also increase the energy of the orbital. So we'll say orbit to respect Niels Bohr's brilliance. So if you increase, as you move out, they come higher and higher and higher energy. So the electron has more and more and more energy. Now, to go to wavelength, I know where I have to go. So this is all number crunching. You would take from there the joules per photon. That is where you plug into E equals H times frequency. And then you can plug into C equals wavelength times frequency, and you will get my wavelength, and that's in the ultraviolet range. But that's what this formula means. And again, this is like 2/3 of the homework set is just going to be number crunching with that and feeling more comfortable with these formulas and realizing it relates. How Damon answered my question, it relates to what we just did. Positive means we're absorbing energy. So instead of saying heat, we're saying energy. If we come up with a negative, it means we're going to be releasing energy. That would happen on the next question. So I lost my blue pen. We'll go with green. So I'm going to, these theory questions, the math questions are wonderful because you get to a number and it's like, okay, I got to a number, and then you get the questions where it's just like, so an electron jumps from n equals 4 to n equals 2. So is the energy change going to be larger or smaller than this change that we just calculated? And why?
It'd be smaller.
It is smaller. Why?
The energy went from 4 to 2, so that's like,
yeah, it's a smaller jump, right? So here we went from 1 all the way to 4. Now we're just going back to 2. We didn't go all the way back. So when the electron, so here we'll do this as like a 2-dimensional. Can you see? You can see over here. All right, so there's the nucleus. And the first layer, n equals 1, this would be a full sphere the whole way around. Each layer gets closer and closer. So the change between layers gets smaller and smaller as you go further out. But once it's out here at n equals 4, so we excited it, it could jump to 3, it could jump to 2, or it could jump to 1. It can do any of those. You can't predict it, it's just what it's going to do. It can't go in between them. But the biggest jump would be from 4 all the way to 1. So 4 just to 2 is going to be a smaller jump. And what else can you tell me about the energy on that? Because you're moving from the outside to the inside. So it's going to be negative. We're going to emit. And so these are called, going back up here, these are called emission lines. When the electron gets excited, we don't see those lines, but as the electron drops back down, it's giving off energy. It gives it off as a packet because it can only make certain jumps. And that packet of energy, which we just calculated here, that packet of energy corresponds to a wavelength. And we see that wavelength with our eyes as a specific line that is a specific color. This one you would not see because it was ultraviolet. This one we would. So I didn't give myself enough room. So the energy, the jump is smaller, so the energy change is smaller. So the second part of the question is the big wrapping up this past hour. Is the wavelength greater or smaller? So if you have a smaller energy change, what's going to happen to the wavelength?
It's going to be larger.
It is larger. It's greater. Goes back. Watch that video. You can dress up as a rainbow as you watch me, and nobody will know that longer wavelength, lower energy corresponds to a longer wavelength. And so it's a smaller jump, so it's a longer wavelength. And it's actually long enough that we would actually be able to see that jump. That would be a violet jump. Would it be? Yeah. All right. Let's move on. That's the math. And again, the math ends up being, even though today you're like, everybody's like, oh, it's just crunching numbers. So this is where it gets really interesting. Again, Niels Bohr, a lot of people put this theory down and say, oh, it's the old quantum mechanics. Oh, it has all these issues. He made the big leap and said electrons exist in orbits. They can only be in specific places. So we're going to expand on that. We have to get through 2 more pages because your study set goes through these 2 pages. So Prince Louis, at the age of I think it was 21, he came up with this, wins a Nobel Prize, and then spends the rest of his life trying to disprove it. But if a wave can knock a particle out, so a wave can act as a wave, light can be a wave or a particle, could a particle act like a wave? That's what he said. He said, well, if a light acts like a particle, then can a particle be a wave? And so this is velocity. That is truly a V. Velocity is meters per second. That is not the same as frequency. Frequency is always just per seconds because it's light. It's a wave. Some people think of it as cycles. This is Planck's constant. This M, we're talking about a particle. It's matter. Matter has mass. And this is wavelength. And he said if you take Planck's constant, which is so extremely small, divided by the mass times the velocity of that, you'll get something. So if you took me or you who's a couch potato, I don't weigh 100 kilograms. Although with my lack of movement, it feels like it some days. And we move like it's about as fast as I moved today. The wavelength that I would be emitting would be, there's no way you could even measure that. 10 to negative 33. That's like a crazy, too small. We can't measure it. I'm sure they can start measuring eventually if they wanted to. But if you take a particle like an electron, holy moly, how do they measure the mass of an electron? Oh, you know, there's this guy who's going to win the Nobel Prize. He's from Italy. He's like amazing. He's really into, he's followed by, anyway, he figured out the mass of a proton to like more digits. And he said the way it was calculated before was wrong. And everybody he was like really young, and he would go to meetings and they all thought, so probably Major's the only one who's going to understand this, but in other countries, the young boys all have to go and get the tea for everybody. And so they thought he was the tea boy, the chai boy. And so he's at a meeting and so everybody's giving him their coffee orders and thinking that he's supposed to go and get everybody their coffee. And he was like the chief presenter for it because he was like this, he'd be like one of you guys there. And he basically recalculated the mass of a proton and said, we've had it wrong. And the way he did it, and it turned out he was right. And anyway, he's got all these, he's really cool. I can't think of his name. Weird stuff comes up for me on YouTube, and he came up. And it's not weird, but some of the other stuff he does is pretty amazing, which gets into meditation and stuff. He's a big time meditator and actually showing these things all go together. So anyway, if you take something with this extremely small mass, 10 to the negative 28 grams, and electrons move a lot faster than you and me at this speed, you can actually calculate the wavelength by plugging into this equation. So you take that mass times this velocity, Planck's constant, and you actually get a wavelength that turns out it's X-rays. And because of that, then somebody develops the electron microscope and everything starts changing pretty fast here. Prince Louis, I'm not sure what else he did in his career other than a lot of these guys then spent a lot of their time trying to, we still don't really understand it. Heisenberg, you've all heard of, his original claim to fame was he actually figured out the math to explain all of this, but the math he used was matrices. If you take one of the calculus, the second year of calculus, you do stuff with matrices, and nobody could understand his math. He almost did not get his doctorate because he could not explain how a battery works. He couldn't explain anodes and cathodes. And so they almost failed him. But he then, many years later, comes up with the uncertainty principle, which is the whole idea. It's impossible to know, and this is, again, me simplifying it, the location and the energy. It's actually the momentum. We'll put that in parentheses. Momentum is actually takes at least a full term, if not a full year of physics to explain. And I don't have that much time. I got 25 minutes of the electron. So if you know where the electron is, you don't know what the energy of the electron is. If you know the energy of the electron, you don't know where it is. This ends up, it's actually a pretty cool math and pretty complicated math formula. He wins the Nobel Prize. It's really controversial because he wins it solo. He was German. And if you look at the time frame of this is right as Nazi Germany is starting to take over all of Europe. Erwin Schrödinger, who's Austrian, right? So Germany goes in and takes over Austria. In 1925, he goes away for a weekend and he comes up with a really famous formula. And so 500 level physics and chemistry classes spend their time, but basically he came back from his weekend away. When he went on the weekend, he took pearls, which he used as earplugs. Can't imagine kind of money people have that they use pearls as their earplugs. With his mistress, so that when he went to talk with his mistress, he'd sit there with his slide rule and figured out all these numbers everybody was coming up with. And we came back, they said, oh my gosh, it explains that periodic table that Mendeleev guy did. And it's like, no, it doesn't. But that's what we're going to talk about. And then Max Born is the guy who his thing becomes even more controversial, is all of this is based off of probability, which is you can never know any of this for sure. This totally blows everything out because, again, going back to Max Planck, they said there's nothing more to figure out. Electrons do not behave like the world you and me see with our eyes. So what Newton did is he figured out the laws of motion, which explains how you and I exist and walk around and stuff. This is electrons. Electrons behave totally different than how you and I behave. Although you and I are made out of electrons. So you can ponder this. It gets into a whole nother, much more interesting lecture. That electrons are behaving like waves. They do not behave like particles. So when we draw this is the Bohr model. First of all, the nucleus would be so infinitesimally smaller than this. And these are the electrons moving around in their orbitals. And this is criticized, except it made that leap that electrons can only be in these orbitals. The biggest problem with this is it's showing the electron as if it's a piece of matter and that it's here. The electron is not there. The electron is a wave. It is all of those places at the same time. It's just not in between. And so you can always go back and make it look like a little bunny rabbit circle and it's running around a track as we're going through this. You can always go back to that, but that's not really what's going on. So what we're going to go through are the layers of where an electron is, and we're going to go back through this again on Thursday. You have a study set with questions on this, the second half of the study set, or last 1/3. We're going to do some questions on this page. And then we're going to do it again at the beginning of class, because this is the theory, and everybody always leaves after the first time we look. This is just like the beginning of the theory part. So these are the terms from Schrodinger's equation. He uses variables. So n, this is like a cursive L. And then the orbitals are given in ML. So the L is the subscript. So these are the first 3 layers of his formula. And they're given really elegant names, and I'm not gonna, so the N is not called the shell, but we're gonna call it the shell because it keeps it simple. It's called the principal quantum number. And so N is a whole number. It can be 1, 2, 3, 4, on and on and on. And it's exactly what I just told you it was. As you increase N, you increase, it's measuring the distance from the nucleus. And again, Rutherford, should have asked that as a question, but Rutherford's the guy who came up with the atomic nucleus, did not win a Nobel Prize for it because the Nobel Committee was not happy with his previous Nobel speech. And the reason he came up with it is he had trouble with it because he kept saying the electrons are negative, they should crash into the positive center. And it was Niels Bohr, it was a conversation with Niels Bohr, and Niels Bohr said, what if the electron can only be at these orbits, can only be at specific places? And that would explain why it doesn't crash into the nucleus. That's our model that we work with today. It's always just going to be a theory. There's no way it could ever be more than that. I don't know how anything can be more than that, actually. So laws of physics, they're right. You increase the energy of the electron. And again, we're going to use the term energy. It is actually the momentum of the electron. So do forgive me if you're a strict physicist in here. All right, so that's kind of back to what Niels Bohr was calling as orbits. So we have the first level, the second level, the third level, and so on. And you can draw. So I had to stay in school because my drawings are not perfect. So this would be n equals 1, n equals 2, n equals 3. You cannot be in between 2 and 3. You can only be at those levels. This math actually works for every element on the periodic table. So they called this, used the variable that Niels Bohr used for that first piece. And so then he added these layers. So we're going to call it the subshell, and it has a much more elegant name. I might have it in my notes. I have like 20 pages of notes here with lots of words. Oh, there we go. We should write it down. This is called the angular momentum. That requires you to have some calculus, or actually trigonometry, sorry, to be able to understand what angular momentum is. So it's not the momentum, it's the angular momentum of the electron. The angular momentum quantum number. All right, so we're going to call it the subshell. So this is where those you had Chem 151, you've heard this before. So this will be, except we're going to go into territory you haven't seen before. L, this is all mathematical equation. L can be any number from 0 to n minus 1. So those are like the limits, you know, you learn about those in math. So it can be 0 to n minus 1, which means if n equals 1, L can be 0. Can't be 1. If n equals 2, L can be 0 or 1. If n equals 3, you guys are seeing the pattern here, L can be equal to 0, 1, or 2. This whole equation that Schrodinger came up with is differential calculus. So that's the end of your second year of calculus. And it was actually easy math, as opposed to Heisenberg's matrices, which nobody could understand. Schrodinger actually put it into differential calculus, which everybody could understand. Anyway, and so on. So what the L number tells you is the number of nodes. And nodes are areas, again, my simplifying it, an area of 0 probability. Schrodinger did not use the term probability. Anyway, and we're going to see that. What it tells us, what the L tells us, because it's the number of nodes, is it tells us the shape of the orbital. The shell tells us the size of the orbital. So again, are you in the first level? The second level gets bigger, the third level gets bigger, the fourth level, we're getting further and further out. And so when L, we're just going to go 0, 1, 2, 3. It keeps going. We're just going to do 0, 1, 2, and 3. These are going to get names, which are S, P, D, F. So somebody gave them names, gave them letters to help distinguish the N's from the L's. So S is a sphere. So it is the shape. It looks like a circle. It looks like a sphere. I can't draw in 3 dimensions. I am trying to remember. I did. You have to go back a couple pages. Oh, I did not. I knew there was one more piece I wanted to add to your notes. They were in our Chem 151 notes. A P looks like a figure 8 or an infinity sign, depending on which angle you're looking at it. This is a node. That is a node. That is what a node is, a point of 0 probability, or it's a place. The other way they define it in math, it's not the best way. It's not a point of symmetry. Let's just go with the 0 probability. What a D is going to look like, there's several ways. a D has 2 nodes. This is the number of nodes. So a D looks, and I apologize, I had thought I'd put the picture in of what all these orbitals, you can just Google it, what they look like. So a D looks kind of like a 4-leaf clover. So there's 2 nodes. So there's 2 planes. And again, it's not a plane of symmetry, it's a plane of 0 probability. So the electron, remember, is running on these paths. Now, Bohr's model, they were always kind of a spherical or circular path. They're not. That is what an s orbital looks like. A p orbital, the path is looking like this. A d orbital, it's looking more complex. And the f would look like an 8-leaf clover. But there's different shapes to them because there's also another way the D looks is a donut with a ball above it and a ball below it. And so there's a node between the 2 donuts. You can Google them, and it just has to do with a way you can make 2 nodes. And so with F, you have 3 nodes, so you can make an 8-leaf clover. So one more piece with the L's is the L also tells you, it's giving you the shape because of the nodes. It also tells you, as you increase the L number, you increase the energy of the electron, or the angular momentum, sorry. So 0, 1, 2, 3, which corresponds to the SPDF that you may have learned in a previous chemistry class. So if I had Major just running around in a sphere, all right, he can do that. And then I tell Damon, nope, you got to do it. And so he's got to do it in the same amount of time. This is more complex. He's got to have more energy to be able to run in his figure 8 or, and then I'm telling Max, he's got to run in a 4-leaf clover, same time. He's going to have a lot more energy because that's a lot more complex. Major's here just doing his nice mellow circle. So imagine like track and field, and instead of the event of being a sphere, you had to run a d orbital. And so you had to run that. Anyway, so where the SPDF came from, the names of SPDF came from, the red line was very sharp. So S stands for sharp. I can't remember P. We'll say petite or perfect. D was defined because everybody can see the first violet line. And then the second violet line is really hard for a lot of people to see. And so it was called fine. And so that's why they called it SPDF, because they actually had names for those 4 lines on the hydrogen spectrum. And it just made it easier to talk about this and easier for me to teach. What the orbital is the ML number. And so this is back again to a mathematical equation. ML can be anything great from negative L to positive L. So if L equals 1, ML equals -1, 0, and +1. I put a positive with it just to make sure you see the difference. You don't have to put the plus there, but ML can be, so these are just, so what does the orbital tell us? We're gonna go back one step. The N can only be a positive number, a whole number. L is a positive number, but it can also be 0. MLs can now be negative to positive L. All right, the orbital, this is called the magnetic quantum number. And it tells you the orientation in space of the orbital. That's, again, me simplifying it so that I can put into words. What this is all saying, oh, and this is where we have probably. So it's the probable orientation. And this is where people were not happy. And some people still aren't happy. You can never it's only a probability that this works. There was apparently, I don't know if anything Einstein said, which ones are real quotes and which are not, because a lot of his stuff was misquoted. But one of his most famous quotes is, God does not play dice with the universe. And that comes down to this, that it's not a probability game. God did not make this a probability game. But it turns out when we get to this point of stuff that we cannot see or perceive, and this is how your phones work, your cell phones. This is what made the technology age. This is why your Wi-Fi will go out in the middle of a test, because it's all based on probability. This is why when your phone is not working, what do? You turn it off and reboot it. You're giving the electrons a chance to all go back to their ground state and start over. So the electrons just, I make the joke all the time too. I'm like, oh, the electrons just made a funky leap, right? So when things do something weird, like a video you've always watched, like I have a meditation I listened to, and last night all of a sudden it did a skip, and I'm like, how can it be? It's a recording on YouTube. It's like an electron made a funky leap. My mom, her Wi-Fi, she moved her computer, and my friend who was like a top network person at the University of Virginia, she like told my mom, open the door between the living room and where the server thing is. And so she opened the door, this door that has always been closed for 30 years, and the signal goes through. They're electrons. A wall is not going to stop them, but it did. So that door is now open that was closed for 30 years. All right, how this goes with the chart. The easiest thing to do is SPDF 1357. You're going to see me do this on the next page many times. Those of you who had been for Chem 151, even you major, you might be going, oh yeah, I remember her writing this on the board 2 years ago. SPDF 1357. You're all going to keep writing that. SPDF is the subshell name. And the 1357 is the number of orbitals. And we're going to go to the next page and just do what you can with the homework. When we go over the homework, it hopefully will start sinking in, and we go through lecture next Thursday, or on Thursday in 2 days. So that was the other thing. Our presentations are not this week. Our presentations are next week. I do hopefully want topics by Thursday or ideas. And yeah, so I know I haven't reposted the syllabus and stuff because I don't believe that I'm not going to have to change it again. All right, let's just go to the page I want. Thank goodness I put page numbers. So I'm on page 58. So presentations, so what day are going to be on the 11th, I believe. That would be the correct day. And so I'll organize when you guys are going to present and stuff. And it was a question Major asked when I had paused recording for a while. Similar like last time, but your talks are probably going to be a little bit longer, or at least as long, because you have a little bit bigger topic. And so you're going to have to present the topic or introduce us to what you're talking about. And I have this thing about the dark side. It's something Omar is awesome at doing, but please make sure you go to the dark side, because there is a downside to everything, or questions on it. Like some of the people in my other class, when we did this, it was like the coolest innovation, and it turned out it was all prototype. When they tried to make it, there was no way they could make it. It was like really great on paper, but we are nowhere near the technology ability to be able to do it. All right, we'll talk about it more on Thursday.
So the presentation has been on Thursday. When is the last, like the last celebration?
It's 2 weeks from today.
So it'd be the Tuesday after the Thursday.
So let's just do this week for right now. So on Thursday, what you have to do is study set and worksheet over this quantum stuff. The lab for this week, I will talk about on Thursday, because yeah. So what you have to do on Thursday is a worksheet and study set. What I found, and yeah, and to look into your topic a little bit. This weekend, what you're going to be doing is getting your topics to make sure you have information. So if you don't, you can switch it around. And then on Thursday, I'll talk about the next week. Okay. But our final celebration. So next week, we will have class on Tuesday, normal like today. That we'll do another study set and another lecture. And on Thursday will be presentations. And then the next week, all we have is the final celebration. And that is just going to be over everything since the last one. And then we're done. So, yeah. All right. So you have questions just like this on your study set. And then you can see we go through more of them on Thursday. So this just asks what is possible, because all of this is based off of probability. It's just what is possible, or the other word you're going to see that is actually the correct word to use is permissible. So because it's a mathematical equation, it's what is permissible. By the way, my gnomes are rainbowed. My mom got me these. I have a thing about rainbows, so. All right. And then if it's impossible or not permissible. So we're going to go through this. And just be patient with yourself. This is so cool, though, because this is quantum mechanics. So the N is our shell. So if we look at all of these, those numbers are fine. They just have to be a whole number. The L is our subshell, which is the shape, right? So the L number has to be less than the N number. So that's okay. So on B, this is no good because the L has to be less than N. That was that rule. So the N and the L cannot be the same. The ML can be the same as the L, but not the N and the L. All right. So B is no good, but A and C are good. So the L can be any number less than the N, and the L can also be 0. The ML, so again, the L has to be less than N. The ML is going to be between positive L and negative L, and it's an equal. It's less than or equal to. So my MLs are okay on any of them. All right, so if it's not possible, you're going to explain why, and this is all I'm looking for, is the L must be less than N. The other way to say it is you can say L is not allowed to be equal to the N. You can say, or N is not allowed to, right, either way. If you get a happy face, if it's good, if it's allowed, you are going to name that orbital. How you name it is you take the shell number, and then, so SPDF, let's write it in purple, going with high frequency. So SPDF 1357. Every time you get to a page, write that down on your periodic table. I guarantee if you have periodic table still from last term, you have it written on there, SPDF. This is the subshell, but we're going to write something above it. We're going to write that the L number is 0, 1, 2, 3. So the number below, the 1357, is the number of orbitals. The L number up here is the number of nodes. And I realize my hand is over that. And in the middle, we just have SPDF. These are the subshell names. You can make them stand. They do go past SPDF now because the theory allows it to go. And after this, they go alphabetical. So G, H, etc. And so we might run into a G, or you might run into one on your homework. So what this is called is the 2, and if the L is equal to 1, that's called a P. So we call it the 2P. So for this one, this would be the 3S, because when L equals 0, that's S, and N equals 3, that's 3. So again, this is the shell. This is the subshell. Where we're going to go with this on Thursday is we're going to put it to the elements on the periodic table. It's this beautiful way of wrapping up the whole term. And again, that's where those of you who had Chem 151, you're going to be like, oh, we're finally back to something I know, or Chem 104 or high school chemistry. All right, so you're going to see a couple of these on your homework where it's the second page after you do the math. So when n equals 3, what can L be? Anybody?
0, 1, or 2.
Yeah, so always start at 0, and then it just can't get up to n. So before we move on, there's 3 possible answers. That's not where I wanted to go with that. Oh, there is. What the n is equal to, that is the number of subshells in that layer. If we were going to name them, I didn't ask you to do this in this question, but they would be called the 3s, the 3p, and the 3d. There is no 3f, because to be an F, L would have to be 3, and the L cannot be the same as the N. So that's like why from the math, the simplifying his mathematical equation. All right, if L equals 3, what can ML be? Well, anything from negative L to positive L. So -3, -2, -1, 0, 1, 2, 3. That's all it's asking. So 1, 2, 3, 4, 5, 6, 7. There's 7 possibilities. When L equals 3, this is talking about F. Going back up to our little cheat thing up here. The cheat thing, you have to understand what it means to be able to use it, and we just have to keep using it so it makes sense. So when L equals 3, that's called an F. F has 7 orbitals. Those are the names of the orbitals with just mathematical numbers. So that's where the number 7 came from. So those of you who took Chem 151, you just memorized 1, 3, 5, 7. But it comes from, in the calculus equation, he has limits on what the ML can be equal to. And that limit is where these numbers come from, which explains why this part of the periodic table has 14 boxes going across from left to right, because this is the F's. All this is going to relate to the periodic table, which is just like the coolest thing ever. All right, so if you have a 3p orbital, n is 3, the L must be, so we go back up here, L is 1, and the ML can be anything from negative to positive L, so the ML could be -1, 0, or +1. Again, you can write +1 or you can just write 1. That's, some people put the positive and some people don't. You're going to see me, sometimes I put it and sometimes I don't. All right. So when n equals 4, L equals 3, and ML equals -2, what do we call it? It's just these 2 parts. The N and the L tell you what the name is. So this would be the 4F. So we're at layer 4, we're on the 4th floor, and L equals 3, that's an F. So this little cheat here, make it into like a note card or something, label it so you understand it, and that's why you have a study set due Thursday. That's part of why I moved the innovations off, because we kind of have to immerse ourselves in this, and then we do the innovations. And all right, we're almost done. So how many orbital, when n equals 3, right? The answer is 9. So this is actually in his equation, that if you take n squared, that is always going to equal the number of orbitals. This only works, I mean, one, it makes me look really smart when I'm standing up in front of the class, and I always know all the answers like that. And I didn't teach you this trick last term, so I got to look really brilliant. This only works if n is all you know. If I give you an L number, you can't use that trick. I'm going to show you why it works for this question. If n equals 3, then L, we actually did this up here. If n equals 3, L is 0, 1, or 2. So we have the 3s, the 3p, and the 3b. So L equals 0, 1, 2. So the 3s, 3p, and the 3d. And again, just write this down because, and then you can go back, kind of ponder it, do the homework, keep pondering it, and just keep pondering it. So when it is 0, there's 1 possible orbital. When we have a p, there's 3 possible. So we have 3, sorry, we have 1 plus 3 plus 5. These are the possible orbitals. For a 3s, there's always only 1. There's 3 possible for a 3p. There's 5 possible for a 3d. There's 5 ways to draw a 4-leaf clover. And so if you add up 1 plus 3 plus 5, you get 9. So if n equals 4, there'd be 16. If n equals 7, there's 49 orbitals. And that's going to correspond to 7 levels out. And that's, oh, they're on the 8th row now in the periodic table. But and that's also why they have to change the periodic table, which they are doing. All right, so how many subshells? When n equals 3, there were 3. We already did that. So that was the 3s, the 3p, and the 3d. And we just labeled them SPD. All right, and then, oh, there we go. The G did show up. So the G subshell. So anybody? How many orbitals must G have? G is the next in the pattern.
9.
Yeah, and so it's 9. We're going to do the MLs. So G must be next. That would mean it has 4 nodes. It has 9 orbitals. So this would be if the L is equal, so for a G, the L is equal to 4. So the MLs are going to be plus or minus 4, plus or minus 3, plus or minus 2, plus or minus 1, and 0. That's the other way you can write it. You can do like what I did up here where I go from negative to positive, or you can just combine them. There's 9 possibilities. All right. Questions before I stop? It's a lot, but it's extremely cool. All right. And